Hi, my name is Vinayak. You can call me Vin. And today I'll be presenting a project that I've been doing with my advisor Josh and my colleagues Maddie and James on object-based synthesis of scraping and rolling sounds based on nonlinear physical constraints. So before I start with the contents of the paper and the research project, I just want to talk about our main research goal with all of this stuff. So we are interested in the question of how humans infer the physical events around them that cause sound. So to answer this, we are interested in this triangle. Basically, how physics around us leads to the sounds we hear, how humans make reasonable inferences from these sounds, and how do those inferences connect back to the physics of the world. This work will be talking about this part of the puzzle, where we will understand how physics of contacts between rigid objects leads to the sounds of rigid objects. And in future work, we'll be looking more on the inference on the computational inference and the physical inference side of it. So talking of contacts between rigid or stiff objects, there are four main types of contacts possible. The first one being impact sounds, the second one being scraping, which sounds like this. Yeah, I plugged it in. Yeah, I plugged it in, the jack. Yeah. Rolling. And compound motion, which is a combination of impact, scraping, and rolling based on the physics of the situation. So I'll first talk about scraping sound synthesis, then rolling sound synthesis. Then towards the end, I'll touch upon how to generate complex sounds for realistic physical scenarios using a combination of impact, scraping, and rolling. So let's talk about scraping sounds first. There have been some well-known approaches to synthesizing scraping sounds in literature. First of which started with Van Doel et al. in 2001, where they read the surface roughness at a sampling rate proportional to speed. Then with Conan et al. In 2014, where they used a source filter model where the source was a sum of successive collision forces convolved with a bank of impulse responses. And then more recently in 2019, from our lab, Trier et al. Gave a physics-inspired source filter model that assumed the sound to be a convolution of the interaction force, which they calculated using Newton laws, and the impulse response of the surface, which was first measured and then identified using a probabilistic generative model. So all of these were pioneering efforts, but they had their own limitations. Most of them had perceivably more rough sounds than recorded sounds. A lot of the times they didn't convey the richness of real-world sounds, and more often than not, some perceptually relevant control knobs were missing. So to address this, we propose a new scraping sound synthesis model, which has physically and perceptually relevant input parameters like motion information, normal force, surface depth information, material properties, and impulse responses from both the surface and the scraper. It goes through differentiable and physically interpretable processing steps, which I'll talk more about in the next slides. And for the impulse responses, we morph between impulse responses on the surface using interpolation in the modal domain, where the modal domain is characterized by the amplitudes, frequency positions, and the decay rates of each of the modes. And then we calculate a net impulse response and a net force, which is then convolved with a modified convolution to give us a final waveform. So one of the key new model features in our proposed model is a physical limit on scraper trajectory. This all started when we found that a lot of previous models had unrealistically rough sounds. What we found is they were assuming the surface profile that you can see in black here to be the same as the trajectory of the scraper point. But that seems to be a generalization, because steep curvatures in trajectory are not physically plausible. We found that you need infinitely high forces to go over some very pointy artifacts in the surface profile. And on closer examination, we found that normal force is the only external force acting on the system that can make something turn on the surface. So the limits on how fast you can turn on the surface were dictated by the normal force that is applied during the scraping process. So to codify this, we put a non-linearity on the surface curvatures in our model. So as you can see in the figure here, which is from real data, z of x is a surface depth map. S1 is a scraper trajectory for a higher normal force, which allows for more closer matching of the surface asperities. And S2 is a scraper trajectory for a smaller normal force, where the trajectory somehow follows the surface, but doesn't follow it exactly. So we wanted to build in this intuition of higher normal force equaling larger curvatures allowed in the scraper trajectories. So for this, we applied a tan h nonlinearity on the curvatures for force computation. You can see the nonlinearity here. So basically, we have this parameter, which is normal force dependent, alpha n, that dictates how much we softly clip the curvatures, which are the second derivative of the depth information with respect to the space variables x and y. So now that we have normal force built in, we also tried to address another issue with some of the previous models. Most of them did not convey realistic motion information. So for this, we modeled the normal force variations for basic human-led trajectories and generalized it. For example, here you see like a force balance diagram, a free body diagram for back and forth motion. And what we found by solving the force balance and the torque balance is that the normal force is maximum near the person who's scraping, and it's minimum away from them. And this systematic variation of normal force along a trajectory seems to be really important for the overall realism of the sound. Like I'll play some sound examples to show that. So this is a recorded version of a PVC scraper scraping over a vinyl tile. And this is how we synthesize it. So you can hear that it's easy to hear in both the recorded versions and the one we synthesized with this normal force variation when the scraper is moving away from the person who's scraping and when the scraper is moving back towards them. So there were three main synthesis ingredients that I talked about. One is a tan h nonlinearity on the surface curvatures that is dependent on the normal force. Second is the normal force variation for some basic human-led scraping trajectories. Third, which I could not touch upon much because of lack of time, was the IR morphing I briefly talked about in the mode parameter space. That also seems to be important to know how the scraper exactly moved on the surface. So to test this, we did some perceptual experiments. We did the first experiment with a mushra-like realism task, where we provided the participants with a text description of the kind of sounds they will hear on one trial. And they hear 7 conditions: 1 full model conditions, 3 model ablations, and 3 previous models from Trier et al., Thoret et al., and Conan et al. And the participants were asked to rate these conditions, which were unnamed, from on a scale of 1 to 7, from least realistic to most realistic. So what we found when we ran this experiment on MTurk for 41 participants is that our model was rated more realistic than all of the previous models, with Trier et al. Coming in second. So the current model performed significantly better than the previous ones on this reported realism scale. So I'll play that again. This was the sound from Trier et al. For scraping over wood. And this was the sound from our model. Again, this was back and forth motion, and you can see that our model represents the change in IRs and also the change in normal force during the back and forth motion much better, which is why we predict that we have higher realism. So then we did another experiment, but this time it was an indirect test. We did a motion discrimination test where we asked the participants to select the most probable path traced by the object. And we also added the recorded sound condition here. So just to give you an idea of what it means to represent like difficult trajectories like, say, a circle, this is what a circle sounds in reality. And this is what Trier et al. Represents the circle as. Because it's constant velocity, and only the normal force and the impulse responses change over that trajectory. And that's the same when we remove the normal force variation from our model. But when you add it, you get something similar to the recorded sounds. So this is what we found, that people are not perfect at discriminating motion from sound, even from recorded audio, but they have systematic confusions, which are replicated by our full model. To test how other conditions and previous models fare against recorded audio in terms of these confusions, we make a similarity metric that compares these confusion matrices. And we found that all the model lesions and the previous models that did not have this normal force variation performed much worse than our full model and the only surface higher condition, which were much more similar to recorded audio in terms of the confusions on this motion discrimination task, suggesting that normal force variation conveys motion information for humans through these sounds. So I'll briefly talk about rolling sounds. Again, there were two main existing approaches: physical modeling done by Rath and Rochesso back in 2005, and Conan et al., who did a similar modeling for rolling sounds, where the successive where they treated rolling as successive impacts, but at a lower impact density than scraping sounds. Here again, there were similar shortcomings, although they were really good models in their own right. The synthesis was not as rich as real-world sounds, and motion and other physical information was not conveyed as clearly as real-world sounds. So the model is very similar to the scraping model. We just have extra term modified from Rath et al. In the contact force, and we take into account more parameters corresponding to the eccentricity of the ball and how the normal force changes for ball motion. We did a similar experiment with the mushra-like realism task as experiment 1, and what we found was that our model and some of our model lesions were rated much more realistic than previous models. Just to give you an idea, this was rolling up a slope from Rath et al., and this is rolling up a slope from our full model. So now that we talked about scraping and rolling, since I have less time left, I will move to like synthesizing sounds for real-life physical scenes. So we have this schema for composing audio for real-life physical scenes that we have also built into our physics synthesis engine that's called 3D World. So we get object configurations, we simulate the physics of the latent scene, then we determine the paths and parameters of sound synthesis, identify when something should roll, something should scrape, or something should impact, and then generate a combination of these contact sounds, which we finally send to our reverberation adding system, and we add it using room impulse responses to get the final sound. So right now we've been using this to test physical intuitions from sounds in humans. Just to give you an idea of some of the physical situations that we have simulated for this, we simulate a ball rolling down a slant and falling on the ground and bouncing to rest, something like this. The good thing is, because of this model, we are able to generate sounds for the physically correct situation, as well as the physically inconsistent situation where a larger ball would roll and a smaller ball would bounce. So this was the physically correct or the physically consistent condition, and this was the physically inconsistent condition, as you could see. And we posed this task on mTurk, where we asked people to select which one of the two was physically incorrect. We had many synthesis conditions and, for many materials. And what we found actually is that humans detect these physical inconsistencies really well. And this suggests auditory intuitive physics, which means that humans store these physical variables from sound. They infer these physical variables from sound and store them over time in object representations to form realistic expectations of what sound should come next. So in summary, I presented new synthesis models for scraping and rolling motions. We used a normal force-based nonlinearity to impose physical constraints, which is basically the scraper not able to follow the surface asperities exactly. And realistic synthesis was substantiated through perceptual experiments. And in the end, I talked about how we can compose complex auditory scenes for studying perception, and we can even use it for game engines or for realistic sound synthesis using physical variables that you can manipulate in real time. So I want to thank my co-authors, Maddie, James, and my advisor, Josh, and I'm open to any questions you might have. Thank you.
Thanks very much. That was very interesting. So I'll start with a question, if you don't mind. I was wondering if you could comment a bit about the efficiency of this system you have, because it seems that you have to do a lot of pre-processing and then convolution integrals. So I'm wondering if this system can be ported somehow to real time, or if you could comment on that.
So that's a really great question. So if you look at the system here, so the thing is that we have built this into a game engine. So we synthesize all of this in real time because there are like a lot of good implementations for faster convolutions and and since we've tried this for frame by frame synthesis of audio and without any lag on like basic computers like MacBooks, I'm pretty confident that if you put it into any real-time game or something, it will work pretty fine. Because you can also try it out on 3D World, which is like our physics simulation platform where actually there is Unity video simulation and audio simulation from these models in the background.
Okay, thank you. We have time for a question, perhaps, from the audience. Yes.
Hi. Very nice, thank you. About the scraping model, I couldn't see the width of the scraping object, where it comes in. Is it a sharp nail? Is it like a mallet sphere or a flat surface? Where do you put it in the model?
So that's a great question. So that's what we are working on now. Basically, right now we have simulated for like smaller contact points. So we don't have a controllable parameter for extended areas, which would be the width of the scraper. So that is something that we are still trying to build in. From some of the initial results, we found that if you actually calculate the sound and you scramble it in some way so that basically, just to give you a physical intuition of what is happening there is there are multiple scraper points like these starting at random times, which gives a more noisier texture to the sound. So that is something that is not part of this paper that we published, but is something we're working on.
One more question.
Hey, you mentioned that you take into account both the stiffness of the scraper and the scrapee.
Yeah.
Is it realistic to assume that there is just one stiffness in each material, given that one of your examples was sandpaper, which is a composite material? Does it make any difference to the sound, is my question.
Changing the surface depth, Matt?
No. You early on in the presentation, you said you take into account two stiffnesses, one for the scraper and one for the surface material.
Yeah, two impulse responses, yes. One for the scraper and one for the surface. And the depth information is only from the surface.
Okay, then my question is invalid.